Yeah, so we started dynamics, right? And we looked at Newton's first and second law. And I think it's okay if we move on now to the third law, right? If everything is clear in it, in its first and second law. Yes, no, is everything clear so far?
Very good, sir.
All right. Now, we said that the sum of the forces, right? Sum of the forces is equal to the mass times acceleration. So sum of forces equal to mass times acceleration. Now, this particular um, letter here is the Greek capital letter sigma, right? And it essentially represents the sum of the forces, right? Some of the forces acting on a system. So we have seen sigma here before. I've seen sigma here before. I've seen this in
Yes, sir.
mathematics. All right. So essentially means the sum of. Now the order of symbols in the last equation doesn't reflect a cause and effect relationship. The net force causes acceleration, right? Not the other way around. So you cannot have acceleration without net force, right? You will never find acceleration before a force. You always have, however, a force causing an acceleration. Now, the SI unit of a force is Newton, and we will say that Newton is that force. Newton represents a force which produces
Sir,
an
sir,
acceleration.
I'm hearing you very low.
And low,
Yes, sir.
we try and back up. All right, so are you hearing me better now?
Yes, sir, a bit.
Yes, sir.
All right, so the Newton is that force which produces an acceleration of 1 meters per second squared. So when it acts on the mass of 1 kilogram, that's the definition of 1 Newton. Now, from F equal ma, right? What is our unit for mass here? What is the unit for mass?
Kilogram.
So kilogram here. And what is the unit for acceleration?
Meter per second square.
All right, so meter per second squared. Let's just put this up here. All right, it's the same thing. Um, so therefore, 1 Newton. Remember the unit for force is 1 Newton. 1 Newton is equal to kilogram. 1 kilogram meter per second squared. All right. So this is very important moving forward. All right. So moving on, let me change the color of this. Right. Now, if we have again F equal ma and say the acceleration. What is the acceleration again? What is the formula for finding acceleration? What is the formula for finding acceleration again? Do we remember?
No, sir.
V minus
Acceleration.
VO over T, sir.
All right. So acceleration equal. That's correct. Change in v over t. Change in t, which is the final v minus the initial v over time taken. All right. So you want to. This is basic knowledge. This is from CSEC. So you should try and really remember this. This is basic stuff. Now, if we plug in this, right, which we'll be doing a lot more plugging in. of equations. But if we plug in our acceleration here, we take this formula and we put it into this particular one, we'll have Vf minus Vi over t. Now we're moving towards momentum. That's exactly what we're moving towards. And how momentum is affected with force and impulse force and so on. But if we take this acceleration and we plug it into our equation and we go ahead now and expand. Let us expand this. Let's say we keep the 1 over t and we expand. What would we have if we multiply this by this and then multiply this by this? Hello? Let's expand this equation. Multiply m by vf. What do we get?
MPF.
MVF
What else?
minus
MVI.
MVI.
What's minus mvi, right? And all of this is
Over
over
T.
t, right?
Yes,
Now,
sir.
do you remember the formula for momentum?
No, sir.
Remember the formula for momentum? So momentum is equal to our mass times velocity. All right. Let me write that out. So I know we didn't have a teacher last year, so this can be difficult, right? But let's see how best we can work around it. So we'll dive into momentum next week. We'll go deeper into momentum with just an introduction purposes. This is our momentum, mass times velocity, m times v. Now this is familiar. Mass times final velocity, mass times initial velocity. So therefore, the force is equal to the. Want to guess what we get here? Mass times final velocity.
The momentum over time.
Right. So final momentum, right? Final
Yes, sir.
momentum minus initial momentum. This is over t. Right. Now, if a body is moving at an acceleration or it's moving at a velocity in this direction, right, it will have an initial momentum. And if it collides with another body which has a momentum, right, if we pay attention to this particular body here and it collides, it will have a final momentum after the collision. So the momentum will change. So therefore, the force is equal to the change in momentum in a particular time. That's what we're trying to get here. So we this pops up back again, our change in momentum. Let me write that properly. Just bear with me for a few seconds, right? And then I'll take your questions. So the force is that change in momentum over time. So this particular body is moving, right? It will release a force during the collision. It will release a force, right? Because of the change in momentum. It will take a force to change that momentum, or it might release another force on this particular. The force might be transferred, right? That's why you have objects. Objects might be separated during a collision. they might be going one direction, and because of the collision, they move to the next one. So this particular object will exert a force other on the other particle, right? Because of its momentum. So that's what we really want to get from this particular slide. So is it clear?
So,
Any
sir, suppose
questions?
the object
Or
not a
is it
momentum,
easy?
sir.
Go again?
So, suppose the object where colliding on a momentum.
So suppose the object collided with what?
Like, say, one car hit one light post.
Right, so it will exert a force on the light force, right? Because of that change in momentum. Remember that the car, let's say this is our light post here, and the car is coming. That's a very good question. The car is coming here. I cannot draw. Right, so don't judge me. So the car is coming here, and it has a momentum of say 20. Now, when it collides, the momentum, let's say the momentum changes to zero because there's no velocity. The car stops at at that particular light post because of that quick change in momentum in a split second. That's the amount of force that will be exerted on this light post, and this light post might even fall over because of that force. So that's how you really relate second Newton's law to momentum. That's how we relate second Newton's law to momentum. All right. Any more questions or concerns? Anyone doesn't understand this? Essentially, what we're doing is
Sir, the last
putting
momentum can be already, sir.
mhm,
Can you please
the
repeat
last
it, sir?
momentum thing. All right.
Yes,
I'm
the
not
momentum
hearing.
can be.
What about it? Where exactly?
Sir, repeat. The last part that you did discuss, sir.
Oh, about the light post? About the light post?
Yes, sir.
Right.
Yes.
So I was saying that you have a light post here, and a car is coming, right, with a momentum of magnitude 20. Just say, for example, it's coming, right, and it collides with this light post. The change in momentum, right, that change in momentum in that split second will exert a force on the light post, and that light post might be destroyed, or it might turn over, it might be broken, or if it's strong enough, it might be able to withstand that force. But what we're trying to achieve is that change in momentum in a split second that will cause a force. That's how we relate momentum and force. All right, is that better? Is that better now? I'm just checking
Yes,
to
sir.
see if any. All right, good. All right, let's continue. Right. So hence Newton's second law can be stated as follows. Right. The rate of change in momentum of a body is directly proportional to the external force acting on the body and takes place in the direction of a force. All right. So because of this rate of change meaning a change in a particular time. Anytime you see rate of change, anytime you see rate of change, it has to do with time. So you want to think about a particular quantity over time, right? Something over time. Anytime you see rate of change. So the rate of change, the momentum of a body is directly proportional. Right? We see that they're in the same line, directly proportional to our external force acting on the body and takes place in the direction of our force. All right. Okay, Newton's third law now. This states that every action has an equal and opposite reaction. All right, this is Newton's third law, and we have seen this before. We have been introduced to this before. Hmm?
Sir, my ear, what I don't know what I mean.
All right, so we'll explain that now. So this law is often misinterpreted. For a correct interpretation, we need to represent the forces of attraction between the two bodies. So we have a man here, this guy, right? So Tyrese is here pushing this particular box, right? This particular box. No, this box is not moving. Let's say this box is not moving, right? What we have object one here, which would be Tyrese, and we have object two here, our box, or let's say wall. Alright, wall. This is our wall, right? So we see two forces into play. Tyrese exerts a force on the wall. He's trying to push this wall, but this wall is also pushing back, right? Or if his force, if he was stronger, right? Let's say we had a box here, right? And we're pushing the box. The force that we exert on this box, right, is should be greater than the force that the box exerts on us, right? And then that would result in us moving the box. So that would cause the the action. That would be the action, all right? Or let's say that's the reaction. So we produce an action, and the object would give us a reaction or an equal reaction, right? Now, this is the force that one is exerting on two. So F12, F12 is the force that the man exerts on the wall, right? And F21 is the force exerted by the wall on the man. All right. So this is an equal. It is exerting an equal force. Therefore, F12 is equal to F21, right? If they were not equal, then there would have been some form of change. As you know, the resultant force would cause an acceleration if they were not equal. Am I correct or am I incorrect?
Okay, that makes sense. Ish.
Yeah. If they were not equal, right? Remember F equals ma. So because they're not equal, then the resultant force that would result in an acceleration. That would cause an acceleration. All right, but because they are not equal, because they are equal, he is putting up an equal and opposite reaction. All right, so is this clear? Is this okay?
Yes, sir.
All right, good, good. All right. Any question? Anyone not clear? Please let me know if you have any questions. Let me know. All right. All right. Let's move on. Now, the force of action and reaction obeys the following. They are equal in magnitude, first of all, and they act in opposite direction. No, remember this one acts, the force that the wall exerts on the man is acting in this direction. Alright, so you should see some simple things in life much differently, like leaning up against the wall. You should look at it now as the wall supporting you, right? It's not just you leaning against the wall. If the wall was not able to produce that amount of force, then of course, that would cause an acceleration of, and you would fall. All right, so these two forces act in two opposite directions. This is the force two on one, the force that two exerts on one, and also the force that one exerts on two. They are in opposite direction. Sec and for the last one, they are acting on different bodies. All right, so they're not acting on the same body. They're acting on different bodies. So the wall is exerting a force on the man. It's exerting a force on the man, and it's acting on that body. While the man is exerting a force on the wall, is acting on the wall. All right, so these are some three basic rules as it pertains to force of action and reaction. Now, the force of action and reaction exists always in pairs and they don't cancel out each other, right? Because the two forces act on two different bodies. So don't ever make the assumption that they cancel out each other, or don't ever make that mistake. Why? Because we made this clear already. They're acting on different bodies. All right.
Same and understand I say the same.
Right. So I'm saying if it was a case where you had one body and you had one man here, you had one man here, and then you have one man here, another guy here, and they exerted the same amount of force, then they would cancel with each other because they're acting on the same body. But they're not acting on the same body here, right? In this particular exercise, these two forces are not acting on the same body, they're acting on different bodies. So therefore, you cannot say that they cancel out each other, right? You can't say they cancel each other. It's just an action and reaction. That's how we have to look on it. All right, these are just some concepts, right? So you don't really have to take it too serious as yet. All right. So is it clear now? Is it everything is okay? All
Yes,
right.
sir.
Yes, sir.
All right. So examples of forces of action and reaction. These are just some examples. I'll just run through the first. I'll do the first one. The Earth exerts a force, a gravitational force of attraction on the Moon, and the Moon exerts a force of the same size on the Earth. Now, we'll go more into gravitation in the future, but as you know, every object, according to the law of gravitation force, every object has um, a gravitational force, or it exerts some form of gravitational field, and this is dependent on the size of the object. Now, in order for the moon to be in orbit, right, of the sun, they have to exert the same amount of force, right? The same size, is the same magnitude of force, and they are acting on different bodies. So that's why you find that the moon exert, it doesn't move out of the gravitational field, right? It's the same thing if we have satellites. You have many different satellites in around the Earth, right? These satellites are in orbit to the Earth, and of course they are placed at different points, but essentially it is because of the gravitational force of Earth and the fact that the size of those um, the size of those particles, or the size of those satellites, are able to exert a force also. That's why there's no movement, there's no resultant force. Those forces are the same size. Action of reaction, um, reaction and action. All right. Now a rocket moves upward as a result of the push exerted on it by the exhaust gases, which the rocket pushes out, right? So it is able to move upward. Say we have a rocket here, right? You will see that the rocket exerts fumes. You see some fumes going out at the bottom of the rocket. So it makes a push downwards, and the reaction of this is an upward force. So it pushes downward. Action, it exerts a force on the earth, and the earth pushes it back. It pushes against the earth, and the earth makes a push towards it, and essentially it goes upwards. All right, it's the same thing when a man jumps off the ground. If you are jumping off the ground, you make a push towards the earth, and then the earth pushes you back. All right, I know it sounds strange. All right, and if a car is accelerating forward, you realize that whenever the cars are moving, the orientation of the wheels is like the car is pushing against the road, right? Pushing backwards, and then the road pushes the tires forward. So if there is no ability for the earth or for the road to push back, if the road is smooth, you won't find any form of movement. But because there is friction, right, you're able to move and accelerate. So you push against the road, or you push against the wall, and the wall pushes you back. Right. So are these clear? Some examples just to give you a better understanding. Is this clear so far? Yes, sir. No, sir. Hello.
Yes, sir.
All right. All right. So we have a couple things to complete here. Let me just. I'm missing a slide here. Can you insert the slide and paste it up? I'm missing something. All right. This one. This is just a summary of all the formulas that we just completed. So, Newton's three laws. Let's look on the first one again. So, Newton's first law, right? Newton's first law. So, the resultant force, right? Remember Newton's first law, which states that an object in motion or an object in at rest will remain at rest. So, therefore, the resultant, or it has to be an external resultant force, resultant force that can cause an object to move. So therefore, there will be no acceleration. Let me just make that clear. Acceleration is equal to zero, right? If there are no external forces. So let's just write an equation that shows that. So that would mean that the sum of the forces is equal to zero, right? Because acceleration is equal to zero. So the object will remain at rest, and the object will, if an object is in motion, it will remain in motion. Got it. So I'm not able to get that back. So I'll just write it again. Alright, so the first law, so acceleration is equal to zero. So therefore, the sum of the forces is also equal to zero because there's no change unless there is a force, an external force. Once the body is at rest, it will remain at rest. All right, the second law states that the sum of the forces is equal to the mass times our acceleration. All right, so they're directly proportional. The force exerted is directly proportional to our acceleration. The third law states now that every action has an equal and opposite reaction. So therefore, F12 would be equal to F21. Alright? And there has to be a negative sign. And why is there a negative sign?
Sir, the bigger number is at different. That's what I see. It moves from F12 to F21.
Go again?
Sir, because it changed from F12 to F21.
Not
I
exactly.
don't know.
Not exactly. Remember that these are in opposite to each other. Alright? They are in opposite direction. That is the reason why it's negative, alright? So
Yes,
this is
sir.
F1, this is F21, which is the force that the wall exerts on the man, and then F12 is the force that the man exerts on the wall. So this is a summary of Newton's three laws, right? Let me see here. All right, we can do one more show with the time that we have remaining. So let's go from the beginning again. Let's say we have the sum of forces is equal to mass times acceleration. And let's say that the resultant of these forces is equal to zero. So let's say the sum of the forces is equal to zero, right? Um, so this is zero is equal to ma, and let's put this over here. Ma equal to zero. Now, what is the formula for acceleration again?
Changing
Changing V over T.
the yeah,
All right, so
changing
change
velocity.
in v over change in t. This is essentially um, vf minus vi over t, right? So therefore, let's put this here. Changing v over changing t. This is equal to zero. Now let's say that the mass. Let's say we have a mass and it's not equal to zero. Let's say we have a mass and it's not equal to zero, and then our time is also not equal to zero, right? But one of these have to be equal to zero for this to be equal to zero, right? Yes or no? Hello? Let me say that again. If you have the mass and it is not equal to zero, and the change in time is also not equal to zero, one of these have to be equal to zero, right? But this for the entire thing to be equal to zero. Yes or no?
Yes, sir.
So which one would it be? Go ahead. Which one would it be?
Which one of them what, sir?
Which one of these is equal to zero? Right? Which one is left? If the mass is not equal to zero and the change in time is not equal to zero, which one is left?
The velocity.
Changing V.
Exactly. So the change in v is equal to zero. So what does that mean? This is very important. What does this mean?
That means everything I so everything I got be zero. Can I multiply?
No. What about the velocity? What is it saying about the velocity?
Um, you know, move like there is no velocity.
Exactly. So it's not raising, It's not increasing and it's not decreasing. And what it stays constant, right?
Yes, sir.
So no
Yes,
acceleration.
sir.
So this proves the first law. This proves our first law, which states that um, if the sum of the forces is equal to zero, where if a body is at rest, right, it will stay at rest until an external resultant force acts on it. Then there will be a change in the force, and then there will be a change in our acceleration. But if all the forces that are acting on the body is equal to zero, let's say we have the mass here. Let's say we have a mass and it is on the it's on the ground. It is exerting a force, you know. It is exerting a force on the ground. What we call that force?
Gravitational force.
Exactly. So the gravitational force, and we it this also acts. The ground also causes a force on the body, right? Do we know this force? It starts with U,
No,
up
upward.
up thrust, right?
Yeah.
Good try. Good try. All right. So this U, so U is equal to G, but the body is not moving. So therefore, the sum of the forces, right? This is acting. So U is equal to minus G, or G is equal to minus U. It doesn't matter, right? So therefore, U let's say, let me say that yeah, I'm correct. I'm correct the first. I was correct the first time. So U is equal to G. So therefore, if we bring over this, we will have U minus G, right? And then because they're equal, it is equal to zero. So therefore, there's no acceleration in this particular case. There's no particular acceleration. But if it's a case where the U was stronger than the G, or let's say that the G, the body was stronger, but let's say the body was strong, it was had exerted a more force on the, let's say, a table, right? The table could break, and there will be an acceleration. But because they're equal, because they cancel out, is equal to zero, and there is no acceleration. So therefore, the final velocity is equal to the initial velocity. Wow. All right. So this is not what we're used to from CSEC, but of course, it's a step up to explain this. So if I say show that there is no acceleration when or prove Newton's first law, you should be able to do this. All right. So is this clear? Any concerns?
No, sir.
All right. Okay, good. So we will go. I think we can finish here. So for today, we have less than 8 minutes, and then next topic will be projectiles. Next topic is projectiles. So we can pause here. So if you have any concerns, you can just let me know now. Any concerns that you have? Have you been have you been reading over? Right? It's very important that you read over this particular. This takes a little extra effort, especially the showings, right? For example, the showings from last week regarding motion and straight line, these require you to go over the notes. All right. Don't wait until last minute to go over the notes. Any concerns? Yes, no, everything clear, right?
sir. So I want to show one more, though it's showing something which is
I hear the
wrong.
question, but your mic is low. Your mic is a little bit. Could you talk up? Or send a message in the chat. All right, yeah, send your questions in the chat. Yeah, send a message in the chat. All right, so I don't see any questions as yet. But in the meantime, let's just for the last 6 minutes talk about projectiles. Right, this is a very good topic. So in kinematics, we studied objects moving along a straight line, straight path, such as the x-axis. Right. So, question. All right. So we were used to objects moving a straight line across the x-axis. Now, a projectile is any object that once projected or dropped, it is only influenced by the downward force of gravity. That is the only force that acts on it. So there's no other force. Once it is released, right, there's no other force acting on that particular body. So there are variety of examples of projectiles. So let's say an object dropped from rest, right? Say here is a projectile provided that the influence of air resistance is negligible, right? And an object is thrown vertically downwards, it's the same thing, provided that the influence of air resistance is negligible, or an object is thrown vertically upwards, right? As we can see in B and C, or let's say B. Yeah, B would be directly upwards, provided that the air resistance is negligible, and then an object is thrown upward at an angle to the horizontal. So this would look something like this. We have the horizontal here, we have the vertical, and then the object is thrown at this particular angle upwards. All right. Let me see here. I don't want to go too in depth and then the time runs up. So we can stop here for today. Go back. All right. And stop recording.